So let's start the class today. We'll be looking at convolution and edge detection. And actually, before we do that, let me do this from blue line. Okay, so today we'll start looking at a specific type of optical illusion or particular feature. Wait, I need to connect. Particular feature of the human visual system, which is interesting, or I at least find it very interesting. More importantly, we'll look at how to use some of the libraries for doing computer vision, in particular OpenCV, which is by far the most popular library for computer vision, robot vision processing. So these are the most common libraries to use for computer vision. CV2, which is the OpenCV bindings for Python, Matplotlib, NumPy, Math, and Random we need anyway. And in this Google Notebook, I also use the skimage library in order to be able to read a file, be given a URL. That's a functionality that's not provided by OpenCV. I guess I could get rid of that one. Let me just try that. And let's take a nice picture from Taiwan. Oh, where did you go on your hiking trip? The hiking trip. What was the mountain that you climbed?
I don't know the mountain name.
or the TRA station?
This is from Gongliao to Da.
Gongliao.
Yes.
Gongliao. Okay. So did you see the tunnel?
No.
No?
No.
You were there, right? You didn't just go to the coffee shop and tell, oh, everybody else go hiking. That's what I usually do.
I want to do that.
All my students think I'm very good at hiking because I always say, oh, we go. But then I just go to the coffee shop. My wife come back 3 hours later, then we go home. I haven't seen any of this. I don't want to use. Train station. I wanted to get a picture of the train station.
The first one is Gongliao station.
Right? Yes. So we'll take this one. Oh, they even have a wiki article. Okay. And which one is copy picture?
Yeah.
This one? Alright, so here's our image. getting an error. Hmm. Okay. Okay, so here's our picture of the Gongliao train station. And the first thing you'll notice is anyone can view, hopefully. Can view. That picture is actually wrong because how many blue traffic cones are there in Taiwan? None of them, right? They should be orange, right? So what happened? Actually, I think this is even a I think this is even in their code snippets. No, I don't. Yeah, if you want to read it directly, you could do that, but I want to usually have it as part of the as part of a HTML figure more likely than not. So So when we're processing an image by the computer or using a computer, the most common representation is okay. Most common representation is that our image consists of a two-dimensional array of picture elements. Those picture elements are also called pixels. Right? So you may have heard that term before. But a pixel is an individual element in your image as captured by your sensor. Now, the image format is in so this is sort of what you would expect. It just means that as you go through the row, each pixel is then there's going to be the next pixel, next pixel, next pixel in memory. So you basically go through one row at a time in order to convert, to store your two-dimensional array in memory, because memory is just basically a one-dimensional array. Right? The most common format for a pixel, and there are several, the most common format for a pixel is in computers nowadays is in RGB or ARGB format. Here you're dealing with 24-bit. ARGB, you'll be dealing with 32 bits. So that means that every image is stored as either red, green, blue channel with 1 byte per color channel. And in ARGB, A corresponds to the transparency. So that's usually not so important when you're dealing with computer vision, because our camera images will all have no transparency. But it's nice to know if you need to do some processing, you can actually store some information with each pixel. So there's other pixel formats and color formats that we sometimes use. RGB 565 would be one where each pixel is represented by 16 bits. And you have 5 bits of resolution for red, 6 bits for green, and 5 bits for blue. So that if you add them together, that gives you 16 bits. That means you only need 2 bytes. So your images will be much smaller. You can also, but also the dynamic range is going to be a lot less. HSV, HSL, and YUV are other formats for pixels. So for processing multi-byte data in a computer, endianness is very important. You need to know the endianness of your data. Either you need to create your own specification, or you have to follow the standard that is used by all the other software that you need to talk to. So what does the endianness mean? You guys know? And there's 2 types of endianness, little endian and big endian. And each processor has different preferences. Little endian is generally considered to be more efficient because you can stop reading bytes as soon as you have all the data. But both of them have been used by different processor companies. So now some of them you can switch. ARM is little endian, I think. MIPS and the Motorola M68K line of processors were big endian. Intel is little endian. So why is that important? Now if you look at the image, you can see that the traffic cones are blue instead of orange. And this problem occurs, or this occurs, if you have the wrong endianness of your data. So what we need to do is we need to swap the, actually I want to make sure I didn't swap them already. Yeah, we need to swap the order of the bytes. So I need to swap from RGB, reading in a 32-bit value, a 24-bit value, as red, green, blue, if which is what it would be if it's big endian. Little endian, it would be BGR. Right? Because it would be ARGB, but A would be the last one. So luckily this can be done very easily in using NumPy. And in fact I can swap the channels like this, which means any row, any column, iterate through it starting from 0 until the end and increment by -1, which means go backwards. So this will flip RGB to BGR. Actually, and NumPy is actually very clever. This is what's called a view into your array. So no data is actually copied. This is a very efficient operation. And you may know that for another area where endianness is very important is when you're dealing with different computers and they need to talk via the network. So the standard for internet connectivity, the IP addresses and that kind of data is all transferred in big endian order, or what's called host endian order. So that way a Mac computer, MIPS processor computer and Intel computer and ARM computer, they can all communicate with each other without getting confused about what the actual IP address is that they're trying to connect to. Because the IP address is sent as a 32-bit integer. So if you read this in little endian, then 192.168.1.5 will be 5.1.168.192, which will be some other computer, not the one you need to connect to. come this one cannot save? So if you're writing programs for the internet, then those would be called network and host byte order respectively. Network, which is what's being transmitted over the network. Host byte with however the data is represented in your computer, in your particular CPU. So now let's try this. So now that looks a lot better, right? Now our traffic cones are actually red or orange as opposed to blue. Right? So now we have the image in the right color format. So now, since we have all the red pixels, all the green pixels, all the blue pixels, all the red color information, the blue and the green color information for each pixel. I want to now implement a function which takes an image and an index for a particular plane, and I can just extract that color channel then. And let's say I calculate some statistics for each plane. So in this case, I take the red, the green, and the blue plane, and I calculate the maximum value, the minimum value, and the average value for all the pixels in that particular plane. Then, in order, I can do things like compress it, so that I can subtract the average. That would mean that the brightness of the three planes will be averaged. Now I want to do that again. But actually, I don't think I need to redo all of this. Then I can extract the various planes, the red plane, the green plane, and the blue plane, and then we're just going to show them. So here I extracted out the red, the green, and the blue channel. And then I just displayed it as a grayscale image, like just as a brightness value. And as you can see, nothing particularly interesting happened there. Or nothing surprising happened there. Also our statistics, the values in the red channel went from 4 to 255, and the average was 143, so it didn't actually do much. So here now I use different compression for the red, green, and blue. So map plane, I can basically change the spread of the pixels in a channel. So it'll calculate the average, and then the range would be from minimum to maximum, but I can make the range from minimum to maximum divided by 2 or 3 or 4 or 5. That's what the compress parameter here does. So I can restrict the dynamic range of the pixels. If I set compress very high, then all the data will be just the average of all the pixels in that particular channel, in that particular plane. So I can replace all the red pixels if I set compress to a very high value, then all the pixels are going to, this term here, plane minus average divided by compress, is going to go towards 0. So every pixel is just going to be replaced with the average brightness of that pixel. So that's what the routine does. So here we have our original image, and now if I take the red channel and I compress it by 2, then the dynamic range is going to be much less, and the green channel I compress by 4, and the blue channel I can compress by 8. So originally, my red plane was from 4 to 255 with an average of 143. Then by compressing it, dividing it by 2, now it ranges from 73 to 198. Still has about the same average, right? It should be the same average apart from rounding errors. The green channel was from 0 to 255, so it used the entire 1 byte of color information, which an average of 139, and then I compressed it by 4. So now the pixel values only go from 104 to 167. And about the same average, and then average doesn't change, and then the blue also from 0 to 255, and 138, and then I compress it by 8, so now the pixels are only from 120 to 152, with about the same average. fix that. Should be snake case, not camel case for Python. So now, also the and here you can see, even though I have much stronger compression, not that much changes visually in the image. So now we can do some interesting things, because I can try and show the effect of compressing various parts of the image. So I read the image, and then for the 3 channels, red, green, blue, I make a copy of the image, then compress only one of the channels. So first just red, then green, then blue. Only red, only green, only blue. And then I take that image and show it in color. Right? What would happen to the color? So now what would you expect to happen. So naively you would think that if you compress one channel in a natural image, if you compress one channel, whether it be red, green, or blue, then the distortion, the effect on the final image should be the same, right? You wouldn't expect that there's some preference on one channel as opposed to another. However, when we actually try it out, let me just make sure that I read this correct image. Yeah, that's right. Okay. Yeah, this image is a little bit bad because I think the slice didn't. No, it didn't. So yeah, this image, it's hard to see because the sky is sort of wide and a major component of it. If I look at the sky in the original image, that's all white. Oh, maybe I cropped the image. So if this is 800 by 600, then let's take from 200, 300, 200 to 600, and from 200 to 600 and 200 to 400. So let's try that. So it's also easy to use NumPy NumPy functions to actually extract parts of the image. So we resize it to 800 by 600. Now here, this is columns, this is rows. But if I use it as a NumPy array, then it will going to be rows first and then columns. And I think I have to copy that now. So let's see what we have. Right, so now I just zoomed in on part of the image. So I want to do that for the rest of the images too. So we zoom in, we implement our function to map. Separate it into RGB channels. Compress the various channels. And here you can see, for example, the cone is very bright in the red channel, right? Because it's very red. In the green channel, it's sort of average and or dark, and in the blue channel, it's also pretty dark. So anything red should have a very strong response in red, but not in the other ones. Now let's look at the compression artifacts. So yeah, now it looks better. Okay, so if you now look at the compression for the red channel, if I compress the red channel, then the colors are way off. If I compress the green channel, the change is even more drastic. Right? The image colors are way off, and the blue channel is actually pretty much less effective. Okay? So what does that actually mean? If we're running this test and now we see this result, so that if I look at the green image, I know immediately this is wrong, right? And I also know the red one is wrong. The blue one, the colors seem pretty okay actually. Right? Much less distortion in the blue channel than in the red or the green channel. So that means that your eyes are much more sensitive to the green channel than any of the other channels. And any distortion in the green channel in particular, and also the red channel, you will notice. But your eyes are actually pretty bad at recognizing blue. detecting blue colors is much harder for the human eye. The response of your eyes to variations in blue is much less than that of for the other color channels. So now I can run the same test, but now I run it with a factor of 400, which means that I basically take the entire image plane and just delete it, replace it with the average color. One byte to represent all of the red color information, and 1 byte to represent all of the blue color information, and the green one respectively. So then you can see the average, after manipulation, the average color for blue is from 84.5 to 85.5, so only 1 unit. And similarly for the other channels. And you can see very strong influence in red and green, and much less impact on blue. If you look at the people, for example, the colors are totally off here. And green, of course, the entire image, you can immediately tell that it's wrong. The blue channel is much harder to detect. You can still see that the color is slightly off, but you're not sure why. So why do you think human eyes are sensitive, more sensitive to green than to red or blue? And in fact, in particular blue. Like here, this is actually an amazing amount of compression that I did on the image. If you think about it, the image has a red plane, a green plane, and a blue plane, and now I threw away one of the planes, right? So I compressed the image by 33%, basically. 1/3 is gone. And I think evolutionary, it sort of makes sense, because most of the things that we care about are green, in the green spectrum. So our eyes develop to identify many different shades of green in order to be able to recognize all the different plants you can eat and you cannot eat. Right? But there's really nothing much in the world that is of importance, in the natural world that is of importance, that is blue. The only thing that you need to know about blue, if you are a Stone Age hunter or a Stone Age mother taking care of the children, is probably around the weather. But then all you need to know is the sky blue or not? You don't need to be able to identify many different shades of blue. And of course, also evolution is sort of limited by the biology and chemistry, so it was probably harder to build sensors, receptors, and tune them to the blue than to other ones. But if that would have given us a evolutionary advantage, then I'm sure biology would have sort of been able to find a way to do that. Evolution would have found a way to do that. But there's no advantage to being able to see blue very well. But green seems to be very important, to be able to recognize different shades of green. Now, there are some genetic mutations that are quite interesting. In particular, for women, there's a genetic mutation which actually gives them, instead of having sort of 3 light receptors, RGB, they have a 4th one. So in their eyes, they actually have more sensitive eyes than other people. And it's kind of funny, because it's hard to explain to somebody what they actually see, because it's hard to describe what you see. It's like trying to explain to a blind person what a tree would look like. Right? It's not something that you can express very easily, or what a blue sky looks like. Not something you can express very easily using words. But these people tried, and the funniest one that was that one of the women said is that she has these friends, and they always come to her and ask her about her dress, whether the dress color matches with the pants color. And her friends all say yes, and she says no, absolutely not. Because she can see the difference in the cyan channel, which is what other people are completely unable to see. There's also some, I'm not sure exactly about the latest research on that, but I think homing pigeons, some of the birds, are able to detect polarized light, like ultraviolet light that has sort of been scattered in a particular way, which is one way in which they can still detect how to fly home based on the position of the sun, even though the sun is hidden behind clouds. So our human eyes are not the only format or the only solution. Other animals have come up with different solutions in order to detect the world and interpret the world around them. Now, this particular realization here that humans are very bad at detecting shades of blue has been used in the JPEG format, for example. You may also notice that effect if you are at night and you're looking at LED displays. Usually the LED displays that are in red or green are much easier to see than the blue ones. If you're going through Taipei City at night and you see the different stores with different LEDs, the green ones are the ones that are easiest to recognize, to read the characters. Blue ones will be the worst. So for example, the JPEG compression standard, so if you have an image that is in JPEG format, then the compression is lossy, so it's not a one-to-one compression decompression, right? When you actually take the original image, then compress it to JPEG, and then uncompress it, you end up with a different image. Certain information is being lost. One of the information that is being lost is most of the blue information. When processing the blue color channel, the JPEG standard actually uses 2x2 subsampling, which means out of every 4 pixels, it only remembers one of them. Like the 4 pixels in a group, it only remembers one of them. So that's pretty good. That means 75% of the data in the blue channel is already gone. So that would be 75% of 1/3, so that would be 3/12. 1/4 of the image is already gone. Before they do advanced processing, what else does the JPEG standard do in order to compress an image to the very small sizes that you're familiar with? Further processing in the JPEG standard is based on the frequency response. Using the discrete cosine transform, if you're interested. So then, the other fact about the human visual system is that actually detecting absolute values, it is not very good, but it's very good at detecting contrast, like small subtle changes. So the JPEG standard uses the discrete cosine transform in order to be able to extract how things change, what the variations are. That way you can also eliminate a lot of the data. That's how you get the very small sizes for JPEG file standard. Another example is common format for YUV. Yeah, that's a little bit different. Oh, and the other example is conversion from RGB to grayscale. How do you think you convert an image from an RGB image to a grayscale image, like just black and white image? Well, most people would say, I have RGB components of a pixel, I need to replace it with a single value. What single value would you choose? Intuitively, the easiest way to do that, or the one that sort of makes sense, would be to calculate the average, right? Like red plus green plus blue divided by 3. That sort of makes sense. However, the actual conversion if you actually test how people respond to what they consider to be the same brightness in gray level as in color level, then is this formula where we have different weighting factors. Instead of 0.33, 1/3, which is what this would be. Right? If I write it with individual factors, then the intuitive one would be 0.33 times R plus 0.33 times G plus 0.33 times B. But the one that's used by the NTSC television standard based on human response to color changes is 0.299 R plus 0.587 times G plus 0.114 times B. So the human eye is actually much more sensitive in the green channel here. Right? Much more weight, about 6 times more weight or 5 times more weight on G than on B. Right? Blue channel is only weighted by 0.114. So that is interesting about the human visual system. It also has practical sort of repercussions. In particular, it shows you how much processing, because when you look at images, you never thought that you're basically blind in the blue spectrum, right? Your brain is compensating for all of this. And I use it because if I need to convert an image to grayscale, right, then of course I could add R plus G plus B divided by 3. That would be, but still I would have to access the entire pixel then, so I have 2 adds plus 1 division that I need to process. depending on what kind of processor you're dealing with and what the exact access patterns are of your applications, this may not be a big deal, but certainly if you're running it on a low microcontroller, on a small microcontroller, you want to be able to do that as quickly as possible. If you do the proper RGB conversion, then it is even worse, right? Because you now have to do multiplying of floating point numbers. And sorry, it's actually 3 multiplications and 3 additions, so 6 operations that I would have to do, either with integers or with the, if I calculate r plus g plus b divided by 3, which is what you would calculate, then it's only 2 additions and a division. Here we have floating point numbers and 3 multiplication, 3 additions. What I usually do is I just extract the green channel and I throw away everything else. Because the green channel, most of the weight comes from the green channel anyway, right? So, and if the image is a little bit too bright or a little bit too dark, then it doesn't really matter for the computer. If you train a neural network based on that, the neural network doesn't care if the image is a little bit too bright or too dark for what it should be like, for your eyes, for your visual system. So, so I do that quite often. I don't even bother with, most of the time I don't bother with, unless you need to display it for Hollywood, like if you need to have super realistic looking images, then of course you need to worry about these kind of color conversion and rounding errors and things like that. But if you just want to detect a soccer ball, then if you cannot detect it in the green image, you're also not going to detect it in any of the other images. If you're looking for the shape. Or if you want to detect, for our scooter, if you want to detect the pylons, right, the traffic cones. If you cannot detect them in the green image, then you also won't be detecting them in the RGB image. That's my experience. That can greatly improve, speed up your processing. Because now you don't have any division or anything. In fact, when you read in the image, that's all you have to do. You can already throw away 30%, 66% of the data, which means you end up with using much less memory. Now, if we want to detect a shape, like the cone here, then, okay, let's have a look at that particular problem. So now let's look at actually detecting objects in an image, because that's one of the many things we want to do with our robots. It's a very common problem. So here we have an image of a ball. So now you should try and follow along. You can copy this particular notebook, but try and use your own image, something with a large pattern. So 1000. So if you went hiking on the weekend, or probably before, you know that Professor Lin, our department head, actually is very good at and likes to take pictures of birds, right? He has all the different birds. So let's say he's asking you to implement the program to detect all the different kinds of birds in Taiwan. No, must be flocks of birds. Okay, let's take this picture. The penguins. Okay, so here's our where do I do download the image? Segment this one. And now I need to read the coordinates. Image view coordinates. I thought I downloaded it already, but open the image toolbar of what? Oh. No, this one doesn't. So I thought I did that last class. Where we got and downloaded it already. Yeah, let's try this one. What is this? 7 UU maybe? Okay. So I want to detect the birds. You want to help Professor Lin to be able to count how many birds there are in the various images to figure out how dominant they are, or if there is danger of extinction or something like that. Then most likely, of course, you could just say you want to look for the blue breast of the bird, right? Now, why would that be a good or a bad choice in this particular problem? What other choices could you choose? The neck, okay. So then you will be, if we're doing blot detection, which means we're looking at color coordinates, right? Then we would be looking at the yellow, right? That's also a good idea. That should also work. I didn't pick the yellow because the area is smaller, right? And the larger you can have the error of the color of interest, the more likely you are to be able to detect it. Like this part here, of course, in this case, we won't be able to detect much blue either, right? So this is a difficult choice. But yes, the yellow one should also work. It's just that there's less pixels of it in that image. So you can use the same tool here, this mobile fish website, and just record the coordinates for the yellow instead of the blue. Or actually, I'll take, since you suggested the yellow, I'll also take the yellow. So let's, now, if I just look and click on a particular pixel, then I get a RGB value, but of course, that value is not going to be the same for every yellow pixel in that image, right? There's going to be some variation due to lightness, shadows, and just noise in the camera. So what you want to do is you want to take a region and then extract statistics from the object for that particular region, and then say anything that matches these statistics should be the object that I'm interested in. So for this area, let's take these two coordinates. To make it easier, we use just a rectangle, so these two coordinates should be 297, 170 and 307, 178. So let's take that. Oh. Okay, so the coordinates are slightly off. Just make sure. Yeah, this is 575 times 436 instead of 640 by 480. That's because it's scaled in the browser. When it's displayed. So we need to change those coordinates a little bit. So let's take that area of interest. So top left is equal to 297, 170. So we define the bounding box, bottom right should be 307, 178. And then I just want to draw the coordinates as this. So multiplied by 6, 4, no, yeah, 640 divided by 575, and this would be multiplied by 480 divided by 436. So here then we can calculate, and now I want to say any pixel that is within that range from red minimum to red maximum, green minimum to green maximum, blue minimum to blue maximum should be what I consider to be the correct color. But now my seeds are wrong. Top left 0, top left 1. Must be integers, none, I have an index missed. So let's see, print marker 1 dot shape. And what's the marker? for 8644. So oh, whoa, okay, good. So why is the C coordinates wrong? For 8644, 330.57. Ah, yes, of course, I cannot use floating point numbers here. They would have to be converted to integers. So this gives us an indication now for that yellow region, what the red minimum maximum, green minimum maximum, and blue minimum maximum values are. So now I can apply that to the image, and I can replace the pixels that match that particular color predicate. So I simply go through the image and then check the RGB values. Now this will give me uh, Okay. So here we have this. Oh. Okay, so our color predicate was bad. Let's just copy the image. One. Oh, EGR. Now it showed it in. So why does this? Plot test. Okay, that image is correct. So now this should just give me one color, which is cyan. So cyan is red and green is yellow. Blue and red is cyan. Oh, this should be yellow then. Right. Yeah. So this is red. Okay. The problem is that image now has some transparency channel, and I'm not sure where that channel is. So if I just take this, and it's set to 1, the transparency, obviously. So that is bad. So if I go G, G, and G, 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 then I should actually get the red channel probably. That is because right now the output image is going to be floating point numbers, and floating point numbers are not scaled from 0 to 1, but they're scaled, floating point numbers are not scaled from 0 to 255. When you plot them as an array, but from 0 to 1. So I need to specify the data type and I need to specify it to be uint8 as 1 byte. And let's see. Okay, yeah, now it's better. So this is red, green, blue. And the colors, let's just make sure we got the colors correct. So red, green, blue component. Yep, now the color is correct, and now I also want to check how many I replaced. Ah. We have the shape. Most likely what's the coordinates here? (575 by 436). So I think I have the wrong coordinates here. So maybe we'll try it without the conversion. Yeah, that's actually better. Hopefully. So now we detected colors that are indicated in blue here for the image, and our blob detection sort of works, except I don't know what the coordinate of the yellow is here, because if I multiply it by and stretch it so that it matches the maybe I plot the area. Yeah. So that means our max. And we copy it, then we do the comparisons. Then we plot the coordinates that we took as our seed. So let's check. Seed. Zero to 3. Yeah. 0, 2, 3. Okay. Oh. How come my bird thing is so far down now? Seed coordinates. Whoa. Yeah, that coordinate is a little bit large. So what happened there? Should be divide here. Okay, so now we have our yellow identified, right? My original seed region was this yellow on the bird. But one of the problems that you see is that we're missing quite a bit of yellow here, right? That's not recognized. So now my threshold is too low to recognize that, right? And also here, and here, and here. So we have false negatives, where we're saying there's no bird there. On the other hand, we also have false positives here, and we have phantom birds that show up here and here. So how do we fix that problem? This is the area that I used. You can also see some false positives in here, the plumage, but also in the environment out in the back here. So now, the problem is, if I ask you to indicate the yellow regions in the image, all of you are going to pick the beaks here that we want. None of you is going to recognize that this area actually is very similar in color to this area. Okay? Because your brain does a lot of the processing to make sure that you don't really recognize absolute colors. You only recognize colors in context. So initially, a lot of our research with the intelligent robots also used color-coded environments. When we started playing soccer with our humanoid robots, one goal was yellow, the other goal was blue, and the ball was red. And the idea was that we wanted to simplify the detection of these objects. Right? Because they are sort of important when you play soccer. Now we've gotten a lot better at this, so nowadays that was about 2012, something around that time. Nowadays ball and goals are all white. Right? So we use a real soccer ball and real goal colors. And things are actually not worse than with the color-coded environments. Even though you think that may be easier, there were lots of problems, just as many problems with color-coded environments as there were with proper ball and goal detection, because basically you need to look at the geometry of what your object you have in the scene. So a lot of teams nowadays, we actually use circle detection in order to detect things that are round and could be the ball in the right size and the right position. And we look for the goal posts, which are long and thin and slender. Looking just for the colors turned out to be very error prone. And in fact, this whole chapter here on blob detection is sort of just trying to show you how difficult it is to use color detection even in simple environments. The other thing that it showed you is that, and that is true for any vision system, for any system in a sense, not just vision, but in particular for vision. This one is very important because, like we've seen here, there's two types of errors, false negatives. Here the pixel is yellow, but I don't recognize it as belonging to the neck of the bird. Here's a false positive. It says this is the same, this is a bird, but there's no bird there, right? Now, any system that we have to balance, when we tune it, we have to balance, and most of the algorithms, of course, you can tweak, right? You can tune them. You need to find the right balance between the type 1 false positives and type 2 errors, false negatives. Now, it's very important that this balance crucially depends on the application that you're implementing, right? Because one without the other doesn't really tell you anything about the quality of the algorithm. Now, when you play soccer, then what kind of error would be more detrimental to the performance of your system? Which kind of errors are more problematic? If it cannot find the goal, then is that more or less a problem than finding a phantom, a ghost goal? Well, if we think about the ball, right? The robot looks around for the ball, it's trying to find the ball. So now there could be a false positive, which means that the robot says, oh, there's the ball, right? So then it will start off and say, oh, I just saw the ball, so it's going to march off. And then bye-bye, the playing field is back there, right? So even if it doesn't walk off the pitch, off the playing field, having a false positive will still be very detrimental to your performance, because the ball may jump here, then he walks this way, then see the ball, now it walks this way, then see the ball over there, now it walks this way, right? So if you have a lot of false positives, then this is very bad for the performance of your soccer playing robot. If you have a false negative, that means that the robot is right there, the ball is right there, but the robot cannot see it. Right? That is, of course, both of them are not good. Right? Clearly, if we could build a system with no errors, we would do that. But in that situation, it usually is not such a big problem. Right? If you see the ball, if you don't see the ball, then the robot just looks around, keeps looking around, there's a shadow, something changes, all of a sudden it detects the ball. When it starts moving towards the ball, now it is at least going in the right direction. Right? It's doing the right thing at that point, every time it sees the ball. If it doesn't see the ball, it's much less active, right? It's much more passive. Most of the time, the robots, if they cannot see the ball, they simply turn a little bit this way, turn a little bit that way. Now that may be enough to actually be able to see the ball now. Right? So this would be what you would think if you think about the problem from the striker perspective. So you want to implement the striker playing robot, right? What about the goalkeeper? I would argue, and when we designed our systems for the goalkeeper, we were much more interested. We were much keener on seeing the ball all the time, even though we saw ghost balls, because the goalkeeper doesn't really walk anywhere. The goalkeeper just stands on the line usually, and if there's a ball shot, then he will dive and he'll stand up again, right? But if you miss a shot on goal, then this is very bad, right? The other team just scored on you. So in that case, we tuned the detection algorithm to have many more, I mean, not that we wanted to have, we tuned it so that we never have any false negatives. We wanted to make sure that anything that looks, any ball they shoot at the goal, our goalkeeper will try and stop. If that meant that the goalkeeper, if you look at the videos, then the goalkeepers will do several saves where nobody shoots. The ball is over on the other end of the field, right? And all of a sudden the goalkeeper goes, oh my God, they're shooting, boom, right? Which looks stupid, but at least, no, it doesn't really matter. You can have time, stand up again, orient with the goalpost, look at the goal, okay, I'm ready for the next shot. So this kind of trade-offs is very, very important to get right in any system that you have. That's also why, for example, a lot of the deep learning literature where they look at the accuracy, how many of the percentage of correct, it doesn't really tell you. If you just says the algorithm is X% accurate, it doesn't really tell you enough information for what your particular application is. Like deep learning, they only say accuracy 90%, 95%. If you say that for any vision system, then I know you're exaggerating your results and you're overfitting them to the particular training set that you use. But more importantly, you don't even know what kind of errors those were, right? You have no idea if you showed the algorithm 1,000 pictures and your error rate is 10%. It doesn't mean that 5% of those were pictures. You're trying to detect pedestrians for autonomous driving. You work for Elon Musk, Tesla car. You're trying to detect bicycles, right? It doesn't tell you if there was a 10% error rate. It doesn't tell you if there were 5 things that it recognized at the side of the road, and it says there's a bicycle rider, but there was no bicycle there, or if it was a guy with the or somebody was riding a bicycle and the Tesla car just didn't see them, right? Now, for a self-driving autonomous car, you have to make sure you never miss any pedestrian, otherwise you may kill them. And I drove with a Tesla just the other week. There were several times, because it shows you, and the technology is very good in a sense. It's quite nice. It shows you the motor scooters, right? But there were several times where it didn't see the motor scooter at all, or it saw it so late that because the guy was driving, right? We weren't on auto cruise control or something, whatever they call the auto driving mode. Like they don't have it in Taiwan yet. They have it for certain owners of Tesla in the US, I think. Only. But it did recognize the bicycle, but it recognized it when the bicycle was already beside the car, at which point it's already too late. Because if the car drives fully autonomously, it would have already run over the guy or the person. Right? So autonomous cars is also a huge difference in outcomes. If it thinks there is a bicycle rider there and it veers out of traffic to move around, it was a plant instead of a bicycle, then that's okay, right? Nothing bad happened in a sense. Nobody got killed. If your car didn't detect the bicycle correctly or a motor scooter, then really bad things can happen. That is why it's also meaningless to say that if you look at face recognition. A lot of technology nowadays, a lot of police departments want to implement face detection algorithms, right, for surveillance. Some states more than others. China very much interested in that. Russia too, right? So, and when you read the police reports, then why they want to have a camera on every intersection to look at people's faces, then they say, oh, it's very good. Like we caught, the picture caught 70% of the criminals that we send through the city, we can catch them. Which means that they have 100 pretend criminals, they let them walk through the city, 70% of them are caught within one day, right? That's sort of the statement that they're making. So is this good or bad? This number, if they just tell you this information, right? If you don't learn anything else in this class, the most important thing to learn is that this does not establish a correlation. Technically speaking, it doesn't establish a correlation. It simply gives you one error rate, right? The error rate for false negatives. It's not a criminal. If they catch 70% of them, 30% of them were not caught. So the error was 30, the false negatives was 30%, right? Fine, so they don't tell you what the false positive rate is. If, in order to catch those 70 criminals, right, or 700 criminals, if we send out 1,000, 70%, 700 criminals, they catch 700 criminals. If in order to do that, they arrested 100,000 people, and most of them were not criminals, but then of course they check, then they find the 700, right? Then this would be a terrible system. In fact, I can easily build a system that catches 100% of all the criminals. How? Like forget whatever dictatorship or us
camera system does. They get 70% accuracy on catching criminals. I can get 100% accuracy on criminals, no problem. I have enough Python programming knowledge to write that program right here. Because all I have to do is, I just arrest everybody, right? In that case, I'm guaranteed to catch all the criminals. But I also catch a whole bunch of innocent people, right? The same thing is true when they talk about lie detectors. They bump up the how good lie detectors are. Lie detectors nowadays, the skilled interrogator can catch 90% of the people that are lying. That information alone is pointless. Because if they just say you're lying to everybody, guaranteed they're going to catch all the liars. Right? They also catch an enormous amount of innocent people. And this false positive rate is something that we really should not tolerate as a society. And it's even worse when it comes to anti-terror technology. Like people, for a while, they were trying to use micro-expressions. So when you go, or they want to install cameras in the seat before COVID, when you were still traveling with an airplane, right? They wanted to install cameras in the seat of your seat in front of you, and that camera would look at you all the time. And the idea is some guy sold the airlines on this. He's going to write a deep learning network that is going to look at your face, and if you look nervous, right, or a little bit shifty, then they're going to call the marshal to come and talk to you and maybe arrest you in the airplane, right? This was the idea. This is what they sold to the airline. Luckily, that system was never implemented because even though those guys were saying, oh, we can catch 30%, 80%, 90% of the people that are that we send in there as terrorists to try and do something bad, the false positive rate was enormous. And the reason for that is too that most of the time luckily you have very few examples of terrorists, right? So even though it may be 70% accurate, right, or 60% accurate, the number of terror attacks on airplanes per year cannot possibly be bigger than 3. In the last years, I haven't heard anything, right? There were like 9/11, and then since 9/11, there was one German plane where the pilot committed suicide and just crashed the whole plane. But that wouldn't have worked then, that system, because the terrorist was the pilot. So there's not much you can do if the pilot is the bad guy, right? But since then, there was one guy that was trying to hide explosive in his shoes. That's why you have to take off your shoes. So let's say there's 3, which is still much too high, but let's say there's 3 per year over the entire world, right? If your accuracy is 70%, then you basically missed one of those already. So in order to be able to guarantee that you catch all the terrorists, because of course it would be very bad if terrorists would be able to do the attack, you would have to, even if your false positive rate is very, very small, 0.0001%, right? but multiplied by 1 billion people that fly every year, that is all of a sudden then hundreds of thousands of people that have the police check out and do background checks and everything. So this would be an enormous societal impact. So when you are dealing with these kind of systems, anytime somebody's trying to tell you something about these kind of issues, you need to know the false positive rate, you need to know the false negative rate, in order to make any informed decision about whether you believe this is a good technology, a good use of technology, or a bad use of technology, right? And secondly, you need to know what the priors are. Basically, what's the probability that the probability that there actually is a terrorist? Right? If the prior is very, very small, then that gets multiplied by, that has a huge impact by your false negative rate then. So any kind of computer vision system, you need to find the right balance between the false positive, false negative error rates, and then depending on your application, usually one type of error is much less of a problem than another type of error. Furthermore, the priors are not 50% always. Right? So if you're implementing some system, somebody trying to break into your house, right? That doesn't happen very often. So in this case, the prior for this happening is very, very small. So that means you need to have a very good false negative rate in order to be a useful system. But if you if you reduce your false negative rate, then that automatically usually means that you will also have more false positives. So for a security application, that's okay, right? You can send the picture to the user on the phone, and you can say, if you think somebody's breaking into the house right now, do you want me to call the police or not? Then they can look at the picture, and then they can say, okay, yes or no, depending on what happened. If this is a false negative, then they can deal with it like spam. If that happens once a month, this is not a big deal. Of course, if you send an image every 30 seconds saying, I think somebody's breaking in, people are not going to use your system. Right? So there's limits to all of this as well. And machine learning, computer vision, lots of applications of technology, any kind of risk mitigation really too, right? Like vaccines, what are the probability that you will get COVID? What's the probability that you will get really sick of COVID? Those need to be managed properly, which is then the more general problem. Okay, good. So that's it for today. I encourage you to use the Google Notebook, try it on your own collection of objects, take your own pictures. For example, detecting cards, playing cards, hearts or diamonds or something like that. You can just take your own picture with a spread of cards in order to see how well that works if you just lose color. And basically you will realize that even though color looks perfect, right? If I look at that chair, I see one red colored chair, that's it. or this chair. I can tell they are the same color. Actually, I can. My brain tells me they are the same color, and it makes sure that I see them as the same color. Even though the individual colors are totally different. This one is in the shadow, this one is in brighter light. But I have previous experience about the world, so my brain says to the eyes, yeah, no. You think they're different, but really they're the same. Implementing that kind of reasoning is what computer vision, intelligent robot vision is all about, in a sense. We want to be able to do the same characteristic. Now, you may have heard something that I haven't covered, we'll discover it later in class, but you may have heard of HSV or HSL color spaces, which are supposed to map to colors better than RGB. They're a little bit less sensitive, that's true. But in general, 1995 to about 2005 was sort of the heyday where people tried to come up with all kinds of different color predicates in order to be able to detect color better. And I designed my own at that time too. But it's pretty clear that whatever color predicate you use, it's way worse than you think. It is really bad to try and use color to detect anything. So most of now we have more powerful algorithms, more sophisticated approaches. So any new project, even with students nowadays, I tell them that they need to look for shapes. Circles, boxes, rectangles, textures, anything like that. If you did, and that is much more robust than any color predicate. It doesn't matter if you use RGB, HSV, cosine transforms, what have you. None of them are really any good for various applications. For some kind of domain, HSV works a little bit better than RGB. For other ones, RGB works a little bit better than HSV. But in reality, you want to get rid of all of them and use other features first, and only then at the last. So our image processing for the soccer domain changed completely from 2000 to 2005. 2000, we would look first for all the red pixels, and then we would group them together. Then we would check the shape to make sure that it matches what a ball should look like, so the width and the height is roughly the same. We check the position and all of that afterwards. That whole pipeline was completely rewritten then, 2005, where we started looking at shapes only and circles. Then we detect the circles. Then we make sure that the circle is in the right size, the right position. And there's no other thing that could distort the color of the circle. Because when you're detecting the ball, one of the things that was bad was that the ball, if it moved over the field line, the orange golf ball would sort of disappear in the field line. Those kind of things you can still figure out if you get the other parts of the playing of the ball, the circular shape. And only at the very last point, at the last step in our pipeline, then I already know it looks like a ball, it has the right size of ball that I'm looking at, it's in the position where I expect the ball to be, and only at the very last instance do we check and say, do I think this could be called orange? And then if it was, then okay. And the only reason why we did that was because sometimes some of the teams had blue balls or yellow balls, and we wanted to make sure if one of the teams forgets that ball on the playing field, that we're not chasing that ball like during practice and things like that. But that was the only thing that we used color for, only at the very instance. Now at that point, I'm already 90% sure this is a ball. So the color predicate that I used for orange was very broad. Is I could that was just this red bigger than the other channels. Then it would be some sort of reddish color, and that was it. Whereas with the other approach, when we started working with RobotVision systems, you had one guy whose only job was to find these 6 parameters for detecting the ball. And that would take days. And if somebody opened the light or the sun came out, all the color calibration was off. So you had to completely redo this. It was an insane amount of work. And everybody hated the guy that was doing the color calibration because they never got it right. But that's because it was an impossible task that you asked them to do. So then you had these false positive, false negative errors that you needed to balance. So then the vision guy would say, okay, now we can see the ball here as long as it's in the center of the playing field. But there's a spotlight there, so if the ball rolls there, then we lose it, right? Now, I can make it find the ball there, but if I do that, I have false negatives all over the playing field here, which means I have phantom balls, right? So then you say, okay, well, never mind, we just don't play in the left corner of the field. We just, if the ball goes there, we give it to the other team because it's on their side anyway. We hope they dribble it back at us. And this basically, this just switching in the pipeline, the order of the steps, was really important for us because before we would spend days, literally 2 or 3 days, just calibrating colors. And you have like different sets of, you record all of the ones that you have, like Tuesday at 2 p.m., sunshine, this many degrees, no clouds. That's the color predicate I want to use. It was a crazy amount of work, and now it's a lot better. Like now we can go to the competition, we don't calibrate colors anymore or anything like that. The system simply works. There's nothing to calibrate. So we have other problems. Motions, battery charge, that sort of thing. But at least we don't sit there anymore and click on pixels in order to say they should be part of the color or not part of the color. Predicate for a ball. This is part of the ball and not part of the ball. Okay, good. Then that's it for today. And I'll see you all